you can hear me all right. Thank you for coming to this talk. I know it's always challenging after lunch with such a beautiful day outside, so really appreciate you coming here to attend a talk about Rust and Lambda. Hopefully, I'm gonna make it worth your while. Okay, before getting started, I'm gonna be showing you today almost like a full tutorial on how to go from zero to production in writing your own very first Lambda in Rust. And I will show you some code examples, so I have the slides already available online, just in case you want to review anything later. So, I'm gonna start by telling you what is Rust. I'm kidding, of course. I think everyone knows what Rust is, right? Raise your hand if you don't know. Great, okay. So maybe a more interesting question is, why do I like Rust? And actually, it's not an easy question, I guess. Everyone probably will give you a very different answer. So I'm gonna try to tell you what are the things that I found in Rust as a language that I really like. So the first thing is this concept of zero cost abstraction. So the idea that the language itself provides some nice feature to make your life a little bit easier, like for example, the concept of iterators, but all these abstractions are built in the language in such a way that they don't add performance. So performance overhead. So basically, if you decide to use a specific feature, your resulting binary is not gonna be slower, or at least it's not gonna be slower than you implementing that feature yourself from scratch. So that's a feature that is very relevant, especially in the context of Lambda, where performance matters a lot. The other thing is strongly typed language with a good type system, and I'll show you some examples about that. It takes inspiration from Haskell, C++, OCaml, even JavaScript and Ruby. So if you know any of these languages, you will find lots of familiar things. And I think this is one of the benefits of being one of the relatively modern languages, so they can easily borrow what they think was good ideas in other languages that we had for the past 30, 50, or whatever years. There is a very good package manager that is built in the language. So for instance, if you compare that to C++ or Go, you don't have such a nice experience for a compiled language. In Rust, you just install Rust and you have this entire tool chain that does all kinds of things. And we will see as well how useful that is when it comes to writing Lambda functions. And there is already a great ecosystem of libraries. I was actually quite surprised about this because Rust is still a relatively new language. I think it's about 10 years in the industry. So I was expecting that there was a lot more of, okay, I need to solve this problem. There isn't a library. Now I need to write everything myself. Actually, so far, as much as I've used Rust, I never had the issue where a library wasn't already available. And generally, those libraries are very high quality. They have very good documentation. They are very well tested. You can go in the repo and the authors are very responsive. So I was actually quite surprised about this one point here. And coming back to the type system, the things that I like the most are this idea of pattern matching, no-null types, and these ideas of option and result type. And I will have some examples in a bit, so I'm not gonna spend too much time here. Now, I'm not the only one who says that they like Rust. Do you recognize this blog, by the way? Do you know who is the author of this blog? So this is the blog of Vernel Vogels, the CTO of AWS. And apparently he's also become a little bit of a fan of Rust. He was writing some Rust programs by himself in the last few months. And in this blog post, you can see him going through the process of learning Rust and building the first program. So it's kind of an interesting read if you are considering yourself to getting started with Rust. Okay, so let's get started. And actually, I want to show you some actual code example. Otherwise, it's going to get a little bit boring. So I promised you that I will talk about the type system. And I want to show a specific feature that I really like. And this is the fact that Rust in its own tries to do the best at the language level to protect you from not thinking about specific edge cases. In particular, every time you call a function or use a method, you might have the case where either you have something that cannot exist, like the idea of a null type, or maybe there is something that can raise some kind of error, right? And in almost every other language that I used, you have to be very aware on your own of this kind of edge cases. You might check the documentation, you might have some kind of auto-completion, you might have some linter, but that's as far as you go. You can easily ignore those edge cases until you actually have an issue in production. Rust takes a little bit of a different approach, and I'm going to show you in this example, which is a very common use case, right? You want to read an environment variable, But of course, there is no guarantee that when the program is running, that environment variable was set. So you're trying to read this region and what can happen, right? In other languages, you will just get a string, and that string will be either the string or null. In Rust, actually, you get a little bit of a more complex type that is called result type, which is basically trying to encode the two possibilities that we have here. The first possibility is the happy path. So the environment variable was set, and we have it as a string. And the other case is like the environment variable was not set, and in this case, it's considered an error. So what can we do here? So Rust forces us to think about those two edge cases. We cannot just read the string and get away with it. Sorry, there is a little bit of delay there, okay. So, and one way that we can do that is by using this match statement. So this is what they call the pattern matching statement. So the idea here is that the pattern matching forces us to explore all the possible paths. In this case, we have only two paths, the okay path, where we say, if it was okay, then we can access the region, and that region is gonna be a string. Or if there was an error, we need to do something with the error. Now, of course, this is not the only way. Sometimes you might want to say, okay, if I don't have that value, I cannot continue, so just crash the program. So in that case, you can use this shortcut called expect. We're basically saying, expect the value to be there, otherwise panic with this error. And if you use expect, it gets a little bit easier because you get the string straight away in the case you are in the happy path. And then the last option is when you say, okay, if the value is not there, maybe I can provide a sensible default. So let me get the value if it's there, otherwise populate that variable with this default, in this case, EU West 1. So the point that I want to make again is that we have these three different options, but whichever choice we pick, depending on how we are trying to solve this problem, the language is making us very aware that there is here an edge case that we need to handle. And I think this helps a lot with preventing lots of bugs and with writing code that when you ship it to production makes you a little bit more comfortable that you are actually doing the right things. Now let's get into why Rust and Lambda together. Like so far I've been talking only about Rust. Let's see why Rust is a very good candidate if you are trying to write Lambda functions. How many people, by the way, have written Lambda functions before or use AWS Lambda? Raise your hand. Okay, perfect. So I'll give you a super quick intro about Lambda. So Lambda is a compute utility that you have in AWS. You can imagine that as function as code. That's kind of the marketing terminology that they use. And the idea is that you don't have to worry too much about the environment where your compute is running because you just write your code as a function, tell the system which events can trigger your function, and then everything else is managed by the cloud provider, in this case, AWS. So you can imagine you write some piece of business logic, for instance, an HTTP request. You can have an event that triggers your Lambda. Your Lambda will respond to an HTTP request. And basically, the provider will make sure that every time that that HTTP request happens, there is an environment that gets created for your function to run. Your function is going to run, create a response. This response is returned to the client. And then you don't have to worry about what's going to happen to this function. Is it going to stay there for a while? Is it going to get killed? You just get billed by the seconds, actually the milliseconds that your function has been running. And therefore, you have a very serverless, if you want, environment to run your code. So why Rust is very convenient in this case? Because if you have a language that is very performant and efficient in terms of memory, that leads to cost saving. As I said, AWS is going to bill you based on the number of milliseconds that you are running your code. So if you can write the same code, for instance, comparing, I don't know, JavaScript and Rust, you can execute it in Rust so much quicker, then of course you're going to be billed for less milliseconds. Your solution is going to be cheaper. And the other dimension is memory. You generally have to pre-allocate a certain amount of memory for your Lambda functions. The more memory you allocate, the more the unit cost per millisecond. So since Rust allows you to solve the same problems that you will solve with a scripting language, but generally using much less memory, that means that you can also reduce the other dimension. So you're basically saving cost on both the two dimensions for pricing. Another thing that you generally hear people complaining when they talk about serverless is cold starts. So the idea of cold starts is that because this is very dynamic environments where your code is running, AWS will just spin up new function as events happen. So basically what can happen is, because AWS needs to create an entire kind of virtual machine environment, put your code there from maybe an S3 bucket, then initialize the entire environment, and eventually your function is ready to run, all of that extra steps that needs to be taken, sometimes it's something that the user can perceive. So if you are calling an HTTP endpoint as a user, you might see that sometimes that HTTP endpoint takes maybe 1 second extra than usual. And if you are doing something user facing, it's actually a little bit annoying sometimes that you see, okay, why is this taking a little bit longer than usual? So it's something that you want to avoid. Any Rust, because you can get very small binaries and they are very fast at bootstrapping your function. Generally, you have the best cold start, so that the least amount of milliseconds for the user waiting. Of course, you can check different benchmarks and they all give you different numbers. I encourage you to do your own benchmarks. What I've seen myself is that it goes between 20 and 40 milliseconds of cold start. And if you compare that with JavaScript and Python, we are talking about 500 milliseconds to even 2 or 3 seconds. Of course, depending on how big is your code, what kind of libraries are you using, and how much stuff are you loading before your function can run. But Rust generally gives you a very compelling standpoint when it comes to cold starts. Multi-thread safety is one of the things that Rust says, like it's the best language ever because we're going to make multi-threading easy and safe. To be fair, this is not really a strong selling point in Lambda. It's very rare that you need to do something that involves multi-threading in Lambda. Of course, it can happen, and if it happens, Rust is a good choice, but I wouldn't say this is like the main selling point when it comes to Lambda functions. And I already showed you some examples about non-null types and great error primitives, and that, in my opinion and in my experience, is basically one thing that when you get used to think about writing code in the Rust way, then you're going to have a little bit more confidence that you are not leaving out edge cases that eventually are going to just throw errors in production. So if all of that sounds convincing, let's go, and hopefully let's try to build and run our first Rust Lambda function in production. But before we do that, let me introduce myself very quickly. My name is Luciano. I have some badges here that I got from AWS and Microsoft. I work for a company called For Theorem. I'll tell you more about that in a second. And if you have been in the Node.js ecosystem, you might recognize my name because I'm one of the authors of this book. By the way, I'm very available on various social networks, LinkedIn, Twitter, Blue Sky. So if you want to connect, I'm more than happy to keep talking even after this conference. So feel free to connect and reach out at any time. Okay, so what do we do at For Theorem? At For Theorem, we are a consulting company. We are AWS partners fully focused on building solutions on AWS. So we have been helping various customers in various industries doing lots of things, including cloud migration, training, cutting down the cloud costs. We even have some use cases, some case studies, published in the AWS blog, where we showcase how we built a serverless first high-performance application that does financial modeling for the insurance market. So if all of this stuff sounds interesting, we are always hiring, we are fully remote, and you can check out more details on those links, or you can talk to me after this talk. One thing that I'm really proud about is that we take a lot of time at For Theorem to effectively create content and share our knowledge. And one of the many things we do is this podcast called AWS Bytes. If you are into AWS, we try to share as much as we can about the things that we learn on the job every day. So check it out. We have, I think, more than 130 episodes at this point. So probably there is something for everyone if you have been working with AWS. Okay, enough with the advertisement. Let's get started. So how do we create our first Lambda function in Rust? Generally, if you have used AWS, you know that you can create almost everything by just going in the web console. And in the case of Lambda, there is a service. You go in the service and you say, I want to create a new Lambda. And then you should see something like this, right? You say, okay, I'm going to provide the function name. I'm going to provide the runtime, the architecture, and take it from there. So what you would expect is that you say, okay, I'm going to click there and select Rust. And then you start to look and it's like, where is Rust? It's not even in this list. We have .NET, we have Java, we have Node.js, Python, Ruby, and Rust is not there. So I guess at this point the talk is over. I've been lying to you. We can go home, right? No, actually, if we squint a little bit more and like you really zoom in, you can see that there is Rust there, and it's saying custom runtime. So we effectively, AWS is telling us, well, it's kind of easy. We just need to create a custom runtime, which maybe sounds a little bit scary, like if you've never done that. So let's try to understand what a custom runtime is in the first place. So we already mentioned what Lambda is as a service, and the idea that Lambda is just a function that somehow AWS is going to bring up in the cloud when needed, and it's going to pass it an event, and it's going to wait for that function to run and provide a response. So of course it feels a little bit magic, but then if we look under the hood, we can actually see and understand how things work. So let's try to do that. And the first thing that we can learn if we do this exercise is that actually a Lambda function is the combination of two different components. Generally speaking, we only focus on the handler part. So this is the actual function that we write, the business logic. So you want to solve a specific problem, you expect a specific event, you're going to write a function that takes that event and does something useful. That's what we call the handler. But then there is another part that is generally hidden. So if you use JavaScript or Python, you never have to worry too much about the runtime, but nonetheless, that part exists. It's just hidden and managed by AWS. But when we want to write our own custom runtime, it is important to understand what that runtime part is actually doing. Now, imagine for a second that you are a Lambda, yourself, a Lambda, and you are just brought up in the cloud, and you're like wondering in like this big room, okay, what do I have to do, right? Why am I here? So what you can do is that there is an API on the other side of the room that is provided by AWS, and that API is something that you can say, hey, do I need to do something here? So you're basically polling for an event, right? And that API eventually is going to respond to you saying, actually, you know, I have this event ready for you in JSON format, so take it and do something with it. So the runtime is coordinating all this messaging. At this point, the handler is still not doing anything useful. The runtime is just making sure that the Lambda has something to do, receives this JSON as the event that needs to process, and then the next step is to pass the JSON into the handler. Now, this is going to be very specific logic. Different languages will have different mechanisms to invoke a function in the specific language. So the runtime is going to be very specific there, knowing how do I translate this piece of JSON into a function call. At this point, the handler can run. So at this point, we are doing something useful. And eventually, we have either a response or an error. It's propagated back to the runtime, and the runtime can send it back to AWS. Now, the reason why we are sending it back to AWS is because imagine this is an HTTP request. So there is a client on the other side of the room, or you can imagine like outside the room, that made the request to AWS in the first place. All these things are happening. Eventually, the response needs to be sent back to the client. So it's important that the Lambda propagates back whatever is the result of the computation. Now, if you don't believe me that this is all that is happening, actually there is a really nice test that we can do to see that all these things are happening behind the scene. So if in that UI that I showed you before, you actually select custom, you are going to see something like this. And this is Bash, by the way, so don't be scared. I was a little bit scared, to be honest. But yeah, if we zoom in, it's actually very well written. There are lots of comments, and it should be easy enough to understand. So we can see that there are immediately two parts here. The first part, the one at the top, is where we are loading another Bash script that contains the handler logic. So this is the handler part. We are just loading an external function that somebody has provided. Then we start on a loop, and this is the loop where we are continuously asking, hey, is there something that I need to do? Is there something that I need to do? And the ask is happening actually here. It's an HTTP request that we do to an endpoint that, if you can see here, is provided by this environment variable. So effectively, in the loop, the first thing we do every time we are looping is give me an event. And this request is going to be pending until there is an actual event ready to go. So we are going to be blocking here until we have something to do. Then the next step is we actually invoke the handler function that we got from here. We get a response. And finally, we send back the response to the same API that we contacted in the first place when we wanted to get the event. So this is literally a custom runtime written in Bash in 22 lines of code, including comments. So it's not super complicated, but you need to be aware that all these things are happening inside a Lambda function every time that you are trying to handle an event. So all of this to say that in Rust, because there isn't an officially managed runtime that AWS give you, you need to think, okay, I need to bring my own custom runtime to be able to write Rust code. And that will be really annoying, but thankfully AWS has already created a custom runtime that is available as a library, so we can just install it and use that. So we don't need to really worry about implementing all this business logic that I just showed you, but you need to be aware that you need to use this library and what the library is doing. So now that we know how to get started, the first thing we need to do is install Rust. And there are many ways to do it, but the way I prefer is through this CLI called Rust App. And the reason why I like it is because it allows you not to just install Rust, but also all the entire tool chain. For instance, if you need different compilation targets, different extensions, if you want to upgrade your own Rust version, once you install this CLI, it can do all these things for you. And the other thing we need to install is this thing called Cargo Lambda. I already mentioned Cargo is the package manager that you get for Rust. Cargo Lambda is effectively an extension of that package manager, so it's going to add additional commands on top of the official ones. And those commands, of course, are all specific to building Lambda functions in Rust. So there is a website, you can go there, check out the installation instructions for the different operating systems, but it's basically supported in all the platforms. Okay, what is the first thing that we can do with Cargo Lambda? So I already showed you that there are a few things that we need to create in order to write our first Rust Lambda function. But Cargo Lambda makes it very easy because you can just say Cargo Lambda init. And as you can see here, you go through a set of questions. And this is basically creating all the code for you. For instance, here I selected, I want to create a function that responds to an event in S3. So every time a new file is created in the storage, there is an event telling me a new file was created and I can run my Lambda function to process that file. The cool thing is that what happened behind the scenes is that all this code was created for me. And also, if you can see at the top, there is a library called Lambda runtime, that this is the library I was showing you before, that was already downloaded and installed and initialized for me. So basically, Cargo Lambda is removing all the boilerplate that you need to write. You just select the event that you want, and you get a very good starting point. So what's happening here? There are a few other interesting pieces. So there is a main function. Every compiled language has a main function. This is effectively the first code that is going to run. And what's happening in this main function is that we can initialize here the things that we want to have available in our Lambda function. In this case, we are initializing the logger. And then that run function that is provided here by the runtime, this is basically that while true loop that we saw before in Bash. So this run is basically looping, and every time that there is a new event, it's going to invoke our function handler. So the function handler is basically where we need to write our own custom business logic. So generally speaking, everything we just saw so far doesn't really matter that much. This is where we are going to be spending most of the time. Now, in this example, it's not doing anything useful. It's just looping over all the new files that were created and just printing them in the console. So maybe here what we can do a little bit more useful is, I don't know, if the file was an image, we might want to create a thumbnail, or maybe if it was a CSV file, we might want to convert that to Parquet, or maybe we can do some kind of analytics, trigger some kind of pipeline. Of course, this is up to you, depending on the kind of business logic that you want to write. Okay, now how do we test this code? This is still all local. So what we can do is we can run Cargo Lambda watch, and this is going to start a simulator locally running on the port 9000, which simulates the Lambda environment. What we can do is that we can say here at the bottom, what I'm doing, I'm sending events to this local simulation. For instance, you can take an example S3 event, and this is going to invoke your local Lambda with that event. So you can see that here is automatically compiling the Lambda function and running it every time we send a different event. And of course, if you want to create custom events, you can also create custom JSON files and send those custom events to the Lambda. So this is really cool because if you ever written a Lambda function in Python or Node.js, it's not that easy to actually simulate your Lambda locally. And actually, even AWS itself tells you, well, just deploy it and test it online. And that sometimes is annoying because the feedback loop isn't really amazing. So it's actually great that with Lambda and Cargo Lambda, you can do all these things locally even before we ship things to production. Now let's look a little bit more different things that we can handle. What are different kinds of request and response types? So far, we only talked about HTTP. We also saw an example with S3, but there is a lot more. The thing here is that the signature that we get is generally going to be a function handler, and here we're going to have an event. This is always going to be Lambda event, but this part here, which is a generic, can be whatever makes sense for your specific use case. So if you're handling things with S3, this is going to be an S3 event. If you're handling SQS, this is going to be SQS. If you're doing HTTP, we will see that there are even higher level abstractions. But what is the response that we are returning? The response is going to be here. So we have a result type, because of course, if we are failing, we can have a specific type of error. If things are going well, we have a specific type of return. Now, this thing here with the two brackets is what is called the unit type, and it's basically saying, well, we don't really have anything useful to return here because we are just processing a file in the background. So this is almost like saying, I'm going to return null, right? This is like an empty type. But the question is, what if I want to use different request type and different response types? And we have quite a few options. The first one is that if one of these events is an AWS integration, so you want to integrate Lambda with one of the other services, there is a library that is the one that is being used by Cargo Lambda behind the scenes when you select a specific event. But if you open the documentation for this library, you can see that there are so many events that are already supported. You probably have to squint, but you can see, for instance, we have SNS, SCS, which is the email system. We have RabbitMQ, we have Kafka, we have Kinesis, we have IAM, we have IoT. So basically all the other AWS services can be a source of event for your own Lambda functions. And the nice thing is that this library is going to give you all the types, so you don't have to know exactly what is the shape of this JSON. You're just going to have an object, and the auto-completion is going to help you to figure out exactly how to use that object. And one example I want to show you is, for instance, if you want to process background jobs, so maybe you have some part of your application that is generating jobs that can be processed in the background. Typically, that could be sending emails, creating analytic reports, scaling images, all that kind of stuff. So things that you don't want to happen in line, maybe in the request response flow with the user, you just want to say, okay, this is going to happen in a few seconds, but wait for it to happen in the background. What you can do in AWS is that you can use SQS, which is a queuing system. And SQS basically allows you to say, somebody's going to put the jobs in the queue, but then on the other side, you can have a pool of Lambdas that as new jobs are available, they're going to start to get the jobs and process them. So when we write this kind of Lambdas, if we write them in Rust, how do we know about the type of events the type of events that are expected here? And also, how do we know what kind of response do we need to return? And there is actually a more interesting problem. Generally, the way SQS works is that it's not going to give you just one job to do, but it's going to give you an array of jobs. So this is basically if you have a very high throughput application, maybe with like thousands of users, maybe here you have hundreds of emails to process. So what's going to happen is that maybe the first Lambda is going to get a batch of 20. The other Lambda is going to get another batch of 20. So basically, you are trying to maximize the throughput. The problem there is that when you start to work on a batch, you have 20 things to do, and it might happen that 19 of them are successful and one fails. So what do you do then? Do you retry all of them? Do you retry only the one that failed? And how do you tell AWS that maybe 19 succeeded, one failed, so please reschedule only that one that failed? Because otherwise the risk is that you end up with lots of duplicated work just because one of the many things you have to do failed. And basically, if we select SQS in that Cargo Lambda init workflow that I showed you before, Cargo Lambda is going to do all of this stuff. So it's basically automatically going to install the event and enable the SQS feature. And then it's going to generate some code that looks more or less like this. So I'm going to quickly walk you through this code. So the first thing to notice is that SQS is being used, and we have the event, SQS event, we have the response, and we also have a specific kind of failure. Let's see how is that useful. So you can see that the SQS event is here, and the response is SQS batch response or an error. Now, what is SQS batch response? So the idea is that we get this batch of things to do, but we initialize an array where we say, for every item that I need to process, there is an ID. In this array, I'm going to store all the IDs of jobs that failed. So I was not able to process those jobs. So somehow I need to communicate them back to AWS. Then we do a loop and we say, okay, I'm going to process every single record, and then this is going to be your business logic. And eventually, if that business logic fails, you just need to push the ID of that job inside this structure. And then finally, outside the loop, we have to respond with this SQS batch response, where we can indicate all the things that failed. So basically, we don't need to do any API call to AWS. We don't need to manually cancel jobs or say that jobs are acknowledged, they are succeeded. The Lambda mechanism is going to do all of that. We just need to follow the type system and say, in this batch, these are the only things that failed. And at that point, AWS knows exactly what needs to be rescheduled and what can be removed from the queue. And I think that makes things really nice. So if you ever use SQS from an EC2 instance, for instance, it's much more complicated. You need to do many more API calls because you need to deal with all of this, acknowledging and saying that something needs to be sent back to the queue in case of errors. Now, what is another option? Sometimes you don't care too much about specific AWS events. You want to create your own custom events and responses. And the most common use case for that is when you create step functions. Anyone familiar with step functions? Raise your hand. Okay, a few people. So, okay, step function, you can imagine it as an orchestration layer. I don't know if you have heard of something like Airflow. It's probably the more common alternative outside AWS. So step function is something similar to Airflow. So you can design your own orchestration and you can have multiple steps. Some steps can basically split the computation into something that can happen in parallel. You can have if conditions, you can have retries. And every time you execute a step function, there is a global state that you can imagine there is an input. And then as you go through the steps, the different steps can basically change data into the state. And eventually you come out with a result. So you can implement like decision tree, you can implement, I don't know, complex pipelines for processing different files. And generally speaking, you can use Lambda as a building block every time you want to do something very custom. So there are building blocks to do common things, but if you have to introduce your own custom business logic, you can create a Lambda. And of course, a Lambda, it will be so specific that the input type and the output type is something that you have to decide, because it will make sense only in your context. Now, this example that I have here is actually something that I built in a live stream, and there is a link here if you're really bored and you want to see 4 hours of me sweating and trying to make this work, you can do that. I don't know if I would recommend. But the use case here is that I manage this newsletter called Full Stack Bulletin. And the way it works is that every week I select content that I think is relevant for that newsletter. I put it in a backlog. And then there is a process, which is this step function here, that takes all of that backlog and creates the first draft of the email. So it's going to scan all the different links. It's going to make sure that the links are all working. It's going to get the preview picture. It's going to get the title, the author, description. And it's basically going to give me a draft that then I can go and edit manually and improve on it. And one of the things that it's going to do is going to check the previous number, so the previous issue of the newsletter, to know, okay, what is the new number of the next number of the newsletter, and what were all the previous links that, of course, I don't need to repeat again in the new newsletter. So this step function, the first thing that it needs to do is fetch the issue number. So it's basically going to go and fetch the home page of the newsletter and check which one was the last one, and the new one is going to be that one plus one. So very simple business logic. And of course, I have other steps, but I just want to illustrate why in that particular use case, what we get here from AWS is very useful. So in Rust, actually, when we deal with JSON, there are a few different ways to manage JSON values. But the library that is most common is this library called Serdi, which is a very generic serialization library. I think if you come from Java, maybe Jackson is the closest thing that I've seen. And it doesn't do anything on its own. On its own, it just defines a very abstract layer of serialization, deserialization. And then there are other companion libraries that will give you the different type formats. So for instance, there is one for JSON, one for YAML, and many other formats. So we can actually use these two libraries together with Rust in Lambda, in the Lambda runtime ecosystem. And basically the way it works is that you can create your own custom structures, and then you add this annotation that says, well, this is going to be coming in JSON, and it's going to have a field called URL as a string. So whenever I try to deserialize some JSON, make sure that you fill in a struct like this. And you can do the same thing with the response. So if you create a response in Rust and you put some value here, then you can easily convert that structure into a JSON string. So again, very similar to Jackson, where you can say, these are my structures and these are the fields that things need to map to. Now what we can do here is that we implement the business logic, and the business logic is very custom. So the request is going to be this custom structure. The response is going to be this other custom structure. So we are getting the URL as the input. We are going to be providing the issue number as the output. So very simple. This is our building block. We write the business logic here. We embed that in the step function, and then we have provided our own custom piece of logic. Now, the next step is how do you, what if you need to handle any kind of JSON? Maybe your function is so generic that anyone can send you random snippets of JSON, and maybe you need to look for a pattern in that JSON. Now, that doesn't happen very often, but if it happens, you can actually deal with this case as well. And the way you can do that is that there is a generic JSON value type, which represents all the possible JSON values. So this can be either an object or a string or a null or an array, or maybe an object with a field with an array inside, and inside this array you can have other things. So this is extremely dynamic, and the problem with that is because Rust tries to make sure that you don't have any edge case. Let's say that we want to read the URL here from an object. What we need to do is say, okay, I want to get the payload as object means, well, this is maybe an object, maybe not. Assume it is an object, and if it's not an object, this is basically means it's going to panic, it's going to crash the entire code. Here you might have like a default, right? Then the next step is, okay, if it is an object, I want to get the field called URL, but maybe that field doesn't exist. So if it doesn't exist, what do we do? Unwrap means just panic. Then that field, is it going to be a string? Maybe yes, maybe not. And again, you need to unwrap. So of course, this is terrible code. Nobody wants to write this code. But if you really need to have full control on how to traverse the JSON, this allows you to be super flexible. So you can use that as well. Okay, I'm going to speed up a little bit because we are almost at the end. I'm just going to show you that if you want to do HTTP Lambda functions, and this is probably the most common use case, at least that I've seen, especially for Rust because of the performance that you get. When you use Cargo Lambda, the first question is actually, do you want to do something with HTTP? Like, is this an HTTP Lambda? And if you say yes, actually you get code that is a little bit higher level. It starts to feel a little bit like if you're using something like Spring, where you have objects that help you to read from a request in HTTP and create an HTTP response. So you can see here that the type is a little bit different. Now it's response body. This is the output. And then we have the request, which is just request. It doesn't contain Lambda event, brackets, something else. And if we take this event, we can immediately read query string parameters and effectively read everything that you would expect to find in an HTTP request. So the method, the URL, query string parameters, path parameters, the body, and so on. And you have this kind of builder pattern that makes it very easy to extract all of this information from the request. Then we create a response, and the response you have a builder that allows you to say, what is the status code, headers, what is the body, and if there is an error, how to use that error. So this makes it way easier to work with HTTP than you might find, for instance, with JavaScript or Python. Because in Python, there are some abstractions, but generally they are not built in. You need to install them as third-party libraries. it's nice to see that in Rust, everything is already built in when doing HTTP in Lambda. Now, the last thing is, okay, we have written all these amazing Lambdas. We are pretty happy. We know how to test them locally. We know how to use different kinds of events, create different kinds of responses. So shipping time, how do we bring these Lambdas to production? Surprise, there are two other commands we can use, cargo lambda build and cargo lambda deploy. The first one is actually pretty powerful because we are building a binary, and you know that compiled languages, they need to match the target architecture. So in AWS, they use Amazon Linux, and you can pick between ARM and x86. ARM is generally cheaper, so generally you want to target ARM if possible. So the problem is, okay, I'm using all kinds of operative systems and processors. Maybe use a laptop at work, maybe use another device for your own personal stuff. It's always a pain in the point to cross-compile your binaries for the right architecture. So cargo lambda actually can do all this cross-compilation for you. So regardless if you're using a Mac, if you're using Windows, you can always easily target Lambda, Amazon Linux, using the architecture that you want. So that's really, really good and saves you a lot of problems. And then you can just say cargo lambda deploy, and that's going to ship your binary to production. I have a little demo here where basically I'm saying cargo lambda build. And by the way, release means that it's going to optimize your binary even more. So it's going to take a little bit longer to compile, but your binary is going to be much more efficient because it's using more optimization. So eventually all of this compilation is going to get done, and you're going to ship that Lambda to production. Now, when you ship a Lambda to production, you can go in the web UI and you can see that the Lambda was created, but there are a few problems with this approach. One is that, of course, your code is just a bunch of random binary. So if you're used to do things in Python or JavaScript, you know you can come here, change a few things, save, and test your new version of the Lambda. Of course, here you cannot do that unless you can edit binary, and then you have my respect. But yeah, you will need to go through a process of changing the code locally, recompiling, redeploying, which is something that can be a little bit annoying, but I think you can easily get used to that because it's way easier to test locally. The other problem is that we didn't get any event created there in the trigger. Why my slides are not updated? Okay, so we didn't get any event created there, and we will need to create the event manually. This is basically because we just said cargo lambda deploy, and the only thing you could do, you could say enable function URL. If you're not familiar with function URL, don't worry too much. It's just a way to get a URL to invoke your Lambda function. But basically, this is the only configuration option we have. If we wanted to use, for instance, SQS, cargo lambda doesn't allow you to say, well, create an event that represents the SQS event. So generally what you want to do infrastructure as code using something like SAM. And I'm going to go very quickly here, but I just want to show you that cargo lambda integrates really, really well with SAM. So there is already a built-in integration. And basically what you can do is define all your infrastructure as code with SAM, and then cargo lambda behind the scenes is going to do the build part of effectively making sure that you have a binary that you can ship to AWS. So this is what it's going to look like. So you write your own YAML saying, for instance, okay, this is a Lambda function. This is the kind of events that needs to trigger my Lambda function. For instance, an HTTP request on this path with a method get. And then when you deploy, if you put this metadata here, SAM knows that you want to build that one Lambda function using cargo lambda. So SAM is going to be the tool that you use for deployment, but behind the scenes is using cargo lambda to do all the building and cross-compilation. So at this point, you can run SAM build. You can also use SAM local start API that creates an entire API gateway locally. So you have like a RESTful API that you can use locally, which is also really nice when you're building APIs. And then you can do SAM deploy when you're ready to go to production. And because I have just 1 minute, I'm just going to skip to the closing notes. So I think that Lambda is great, and hopefully you knew that already. Like if you like serverless, I think Lambda is a really good tool that you can use. Writing Lambdas in Rust is still something that not many people are doing, but there are lots of benefits, especially if you're looking for extreme performance or if you're trying to save cost. Maybe you have a Lambda that gets invoked millions of times per day. If you can reduce the cost of that Lambda to, I don't know, 50%, that might be a huge saving. Or maybe this Lambda has very bad cold starts and they are affecting your users. If you can reduce the cold starts, that's a perfect use case for considering Rust. And the other thing is that generally Lambdas are very small by design, because you will probably have lots and lots of Lambdas. Every Lambda is like a single purpose kind of thing, maybe 100 lines of code at best. So rewriting that one Lambda in Rust is not like a big effort. You don't need to be a Rust expert to do that. You don't need to know all the advanced features of Rust. You can focus on those 100 lines, and probably you're going to get very far just by doing that. So hopefully I gave you a few examples, but if you want to see more examples, I have this entire open source project where basically I am monitoring earthquakes and sending me notifications if there are earthquakes close to where my family lives. So you can take this code, it's like a fully fledged serverless application, and check it out. All the Lambda parts are written in Rust, but there is a lot more happening there. Then I have another example, which is an entire API gateway authorizer. So if you use API gateway and you use JWT tokens coming from an IDC provider, this library, actually this Lambda, will do all of the validation in a very performant way. I actually originally wrote this in Python, and then just because it was being used millions of times per day by one of our customers, I wanted to rewrite it in Rust just to get the extra performance. And I was a bit disappointed to see that it was only 3 times cheaper. I was expecting like 10x. And then I went and investigated the Python code, and that Python code was basically using behind the scenes a Rust library to do all the cryptography stuff. So really the gains here are more on the runtime part, but the code execution in Python was already quite efficient. So if you're coming from a more generic use case, I think you could expect even better performance gains. By the way, the benchmarks are all available online if you want to see the way I did it. And then if you want to do more, I am actually writing a book. The book is already available, although it's like an early access type of thing. So there is right now a huge discount available if you're curious. There are 6 chapters already published, but we are planning to publish, I think, about 12 chapters to cover all the topics that we want to cover. And you can check out the website to get all the details of that, or you can ask me later. By the way, if you like the mascot, I have stickers, so come and talk to me afterwards. So that's everything I have. I don't know if we have time for questions, but yeah, thank you very much for being with me today.